Hello, my name is David Barnette, and I'm here to give a presentation about my project on pattern recognition of color in images. So I'm going to briefly just go over the problem that I'm trying to solve and discuss some of the algorithms that I chose to use to solve those problems, and then discuss some results and then show you the code. Just to set a baseline, the images that were read into the MATLAB were in RGB color space. And RGB is a way of showing colors with 3 dimensions, where you're showing the contribution from red, green, and blue color to make the final color. So if we're trying to do pattern recognition, we're trying to get a computer algorithm to classify data into different clusters based on characteristics of that data. So if we're trying to classify colors together, we actually want to classify them the way that humans would classify the colors if they were looking at an image. The issue with RGB space is that they easily define any of the colors, but they don't define it in the same orientation, the way that the data correlates with each other, the same way that humans would correlate the colors. This can be seen here in the shades of green. Any of the colors that have no contribution in the red and blue realm are going to be perceived by humans as green. At different magnitudes, some lighter and darker, but if you just take the Euclidean distance between those points, and you can find other points just like this yellowish point at the bottom that will be the same distance but won't be green at all. So that's where the problem comes in, trying to classify based off RGB coordinates. One way to solve this is to convert it into a different color space. One such color space is LAB color space, which the 3 dimensions that it uses to define each color are the lightness and then 2 color opponent dimensions. So this way the A and B can describe colors, while the L dimension describes how light or dark part of the colors are. So one of the ways to solve the classification stuff is to do it in LAB color space, so that you can closely correlate data together the same way that humans would. So the 2 ways that I used classification were for chroma keying and color segmentation. So chroma keying is where you have a background of a single color that's called the key, and you replace every pixel with that color with a different background. So the first way I used to determine the key was to use k-means on LAB space. So I converted the images into LAB color space and then used just the A and B data to do k-means clustering. K-means clustering, and just a quick overview, is where you take values and you find distances between them and cluster centers. And in this case, I used 4 cluster centers. And then once you determine all the which cluster center that each data point is closest to, you then average all those points together for each cluster center, and then that'll become the new cluster center, and then you repeat the process with the new cluster centers. So we repeat the process 3 times to get our 4 sets of clusters, and then we replace the clusters that have the closest value to the key that we chose with a background image. The second algorithm I used to do the chroma key is axis rotation. So in this case, I actually kept it in RGB space, but I rotated the axis in 3 dimensions so that the key color ended up being on the x-axis. Once I get that to the new coordinate system, I convert it to polar, and then any pixels that were in a certain angle of the x-axis are considered to be near enough to the x-axis to be replaced, and those are the pixels that will be replaced by the background. So here are the results from the chroma key. The top image is the original image I used, and it's a guy standing in front of a blue screen, and there's a little bit of background behind the blue screen. And on the bottom left corner, you can see the indices from the k-means clustering. As you can see, the gray is the cluster that most resembles the background that we're trying to replace. So those are the pixels that are going to be replaced. On the bottom right corner is where you see the axis rotation. So it actually goes through 2 iterations. The first time you go through, you get all the values that are close to the key that the user input. The algorithm then takes the median value of all those pixels that were considered near the key, and the median value is assumed to be the actual key that's closest to the real background, and then the algorithm runs again, so you can see there's two results there, and the good angle 2 is the final result that we use to replace the background. So here are the results. The top two images are respectively the k-means algorithm and the axis rotation algorithm's replacement of the background. Very similar in the way that they performed. The k-means takes a lot longer. It's more like 9 seconds, while the axis rotation is under a second. The only real difference you can see is that the background is slightly darker on the axis rotation one, and that's exhibited below. As you can see, the difference between the blue and red ones on the bottom, the blue is the original image and the red one is just a solid red replacement of the background. And you can actually see the shadowing and stuff because the axis rotation algorithm saves the value of the magnitude on the x-axis that we rotated to, and then adds that to the background so that you actually get the shading and lighting effects on the new background. So the other way that we use classification in the color world is to do color segmentation, just to group groups of colors together, and this can be used for computer vision to help identify objects and stuff, but the final output of mine is more simplistic, just like a bonus version of the chroma keying, but I just replace each cluster with a new texture. So the first algorithm that I use for this color segmentation is the exact same as algorithm 1, just using the k-means and LAB color space. And I just group it into 4 clusters, but this time, instead of just replacing one of the clusters that's close to the key, I just replace each of the different clusters separately. And there at the bottom you can see that I just replace the clusters with different textures. The fourth algorithm I use and the second one for color segmentation is just using grayscale thresholding, and so I just convert the image into grayscale, threshold it into 4 groups, and then replace each of those with the new texture. So these results are fairly interesting because based on what kind of vision you're trying to get for some kind of computer application, you would use a different algorithm. So we'll look first at the blue box. So the blue box is kind of there to represent a space where there's red and green. So you can see the strawberry kind of in the bottom right and the green kind of in the upper left. So if you look at the top middle, you can see there's a distinct differentiation between the red strawberry and the green kind of background fruit. But then if you go below that to the gray thresholding one, the difference between the red and green is not evident. So in this case, k-means was able to distinguish between red and green fruit, but the grayscale was unable to do that. But then if you look at the red boxes, in the original image you can see the top red box is around a light part of the strawberry that's very white, and the bottom red box is surrounding a few blackberries. So if you go to the middle top image in the red boxes, you see they both end up classifying as the same object. The white and the black end up being close enough together in 8 LAB space because they don't care about the lightness of it. It's just the opposition of the color elements that they actually classify as the same object, so you can't differentiate the black objects from the white ones. While if you look at the grayscale thresholding, it is very easy to distinguish between the white and the darker blackberries. So in this case, if you were trying to distinguish blackberries from the rest of the fruit, you would want to use grayscale thresholding. So it really is application dependent on which one you want to use. The column to the furthest right is actually where I clustered it into 8 clusters rather than just 4 clusters. And I did this just to show that the ability to differentiate between green and red and black and white is not changed by adding more clusters. So there is a trade space of how many clusters you need to solve the problem, and because the less you have, the less processing power is going to be required to solve it. So here's just what I did is just took those grouped values and just replaced them with the textures. In the top image, that's the k-means one. It's easy to see the green was kind of replaced by that red texture, and the red was replaced by this bluish texture, so you can kind of differentiate between those types of fruit. While in the second texture image, the grayscale one at the bottom, you can see the blackberries very well in the red texture. So right now I'm going to go ahead and go through some code so you can see how it works.